Welcome. In this lecture, we will discuss temperature, heat, specific heat capacity, thermal expansion, and specifically the expansion of water. First, temperature. Temperature is the quantity that indicates warmth relative to some standard and is related to the average kinetic energy of the particles within the medium in question. Temperature has no upper limit, but it does have a precise lower limit. Temperature can only be defined macroscopically. Since it's based on an average, I can't tell you the temperature of a single atom or a single molecule. I can, however, tell you the kinetic energy of a single atom or a single molecule. And to get the temperature, we add up all the individual kinetic energies of all the atoms and molecules and take the average and multiply by some constants, and that's how we get the temperature. So you see in this relationship, the temperature is proportional to the average kinetic energy. So again, temperature is not related to the total kinetic energy, but the average kinetic energy. For example, if we have a bucket of water and a cup of water, the bucket of water will have a higher total kinetic energy and the cup will have a lower total kinetic energy, simply because in the bucket there are more atoms to have energy and in the cup there are fewer atoms to have energy. But the average between those will be the same, and therefore the temperature will be the same. And this, of course, assumes that the water poured into the bucket and the cup both came from the same place at the same time. But how is temperature measured? We're not really going to get and calculate every single atom and molecule and then take the average. So that would not be possible. But we also can't rely on our senses, can we? Have you ever tried putting one finger from each hand into water of different temperatures as shown in this picture, where you put one finger into the cup holding cold water and placing the finger on the opposite hand into a cup of hot water. Then after the fingers have acclimated, you bring both into the warm water in the middle at the same time. Interestingly, the finger that had been in the cold water senses that the warm water is hot, but conversely, the finger that had been in the hot water senses the warm water as being cold. You may have played a similar game with yourself when you were a child. You would go from the swimming pool into the jacuzzi and vice versa to get the renewed and shocking sensation of hot or cold. Even though the temperatures of each body of water had not changed, your sense of the temperature had changed. So the point I'm making is we must refer to some objective reality rather than our own identifications of hot and cold to properly determine temperature. The fact of temperature does not depend on your feeling of temperature. Also note that most materials expand when temperature is raised and contract when temperature is lowered. Hence, most temperature measurements rely on that objective reality to determine a value of the temperature. And this is where thermometers come in. Thermometers, 1, measure temperature by means of the expansion or contraction of a liquid in a glass tube, and 2, they measure their own temperature. Now regarding the first point, one exception is an infrared thermometer, which operates by sensing infrared radiation rather than directly relying on expansion and contraction of materials. But the typical thermometers that we see do in fact rely on expansion and contraction of the liquid inside of them. Regarding the second point, normal thermometers, those that rely on the expansion-contraction, settle on a proper reading only when the thermometer and the substance the thermometer is reading reach thermal equilibrium. That is, they reach the point at which they both have the same average kinetic energy per particle. Why is this significant? Because it means energy is traded between the thermometer and the substance, which could mean the substance's temperature is changed during the process of measurement, meaning the measurement itself no longer reflects the temperature of the substance prior to the measurement. A good way of ensuring that this fact does not invalidate your measurement is to make sure that the thermometer that you are using is much, much smaller than the system you are measuring. Now there are 3 primary temperature scales, the first of which is the Celsius scale. The Celsius scale is the international scale, where the number 0 is assigned to the temperature at which water freezes, and the number 100 is assigned to the temperature at which water boils. Now those 2 values are for the freezing and boiling of water at sea level. The The space between those two values is divided into 100 equal parts called degrees. Therefore, this type of thermometer has been called a centigrade thermometer, from centi meaning hundredth and gradus meaning step. Now, however, it is called a Celsius thermometer after the Swedish astronomer Andreas Celsius, who first suggested the scale. Now, the temperature scale popular in the United States is the Fahrenheit scale. On this scale, the number 32 is assigned to the temperature at which water freezes, and the number 212 is assigned to the temperature at which water boils. This scale originated from German physicist Daniel Gabriel Fahrenheit. The scale favored by scientists is the Kelvin scale, named after Scottish physicist William Thomson, 1st Baron Kelvin. This scale is not calibrated in terms of freezing and boiling points, but rather in terms of energy. The number 0 is assigned to the lowest possible temperature, known as absolute zero. At absolute zero, a substance has no kinetic energy to share. That doesn't mean it has no kinetic energy. It simply can't give up any more of its energy to things around it. On the Celsius scale, absolute zero corresponds to roughly negative 273. On the Fahrenheit scale, absolute zero corresponds to roughly negative 460 degrees Fahrenheit. We can then also write the freezing point and boiling point on the Kelvin scale, and we can draw some dashed lines showing the equivalence of these different numbers on the different scales. Problem 1. There's twice as much molecular kinetic energy in 2 liters of boiling water as in 1 liter of boiling water. Which will be the same for both? A. Temperature. B. Thermal energy. C. Both A and B. And D. Neither A nor B. So we are essentially being asked whether the temperature is the same between these two, or the total kinetic energy is the same between these two, or both are the same, or neither are the same. And of course, temperature will be the same. So the average kinetic energy will be the same between these two, but not the total kinetic energy. Heat. Heat is energy transferred from one object to another due to a temperature difference between them. Importantly, matter does not contain heat, it contains energy. Heat, just like work, is just energy in transfer. The common symbol for heat is capital Q. Energy in the form of heat never flows spontaneously from a lower temperature substance to a higher temperature substance. Energy is always spontaneously transferred, at least in the form of heat, from hot to cold. And we can take an analogy with water, where you have water at a high potential energy always spontaneously flowing to some location at a lower potential energy. Water will not flow uphill by itself, regardless of the relative amounts of water in the reservoirs. Likewise, energy in the form of heat will never flow from a cooler substance to a hotter substance by itself. Now, you could force it to flow, just like you can create a pump and shove this water uphill. You can force energy to go in the opposite direction. That's what we see with refrigerators. But naturally, on its own, energy will always flow from the higher temperature substance to the lower temperature substance. Problem 2. The same quantity of heat is added to different amounts of water in 2 equal-sized containers. Assume the initial temperature is the same. The temperature of the smaller quantity of water, A, decreases more, B, increases more, C, does not change, or D, not enough information. Well, the answer is clearly B, increases more. An explanation is that there are fewer water molecules in the container with less water, so each molecule receives more energy on average. Although the same quantity of heat is added to both containers, the temperature of the container with less water increases more. Internal energy. Internal energy is the grand total of all the energies contained within a substance. The common symbol for internal energy is U, not to be confused with the U that we use typically in our course to represent the potential energy. So we must be aware of the context of where our symbols are used. Internal energy is an extensive property, that is, its magnitude depends on the amount of substance. So it's not an average, it's a total. It can be changed by adding heat or doing work on a system, and we will talk more about this in a future chapter when we introduce the first law of thermodynamics. Now, no matter how cold an object is, it always has some internal energy. Specific heat capacity. You can touch the aluminum pan of the frozen dinner soon after it has been taken from the hot oven, as shown in this picture, but you'll burn your fingers if you touch the food it contains. The filling of a hot apple pie may be too hot to eat even though the crust is not. Why are these two scenarios things that we experience? How do we describe this? We describe it through something that we call the specific heat capacity, which is the tendency of a substance to resist changes in temperature. The common symbol is lowercase c, and you can think of specific heat capacity as something like thermal inertia. Now, the greater the specific heat capacity is, the more energy is required to change a substance's temperature. Consider, for example, a pot of water, a pot of iron, and a pot of silver, where the water, iron, and silver all have the same mass, and all three of these are placed on a stovetop, and the flame is turned on. And we want to know which one will reach, let's say, 100 degrees Celsius the fastest. Well, let's say the pot of water took 15 minutes to be heated from the room temperature, let's say, to its boiling temperature. The iron of equal mass on the same flame would rise from room temperature to, let's say, 100 degrees Celsius, which is the boiling point of water, in only 2 minutes. For silver, the time would be less than a minute. In this example context, we say the water has a higher specific heat capacity than iron and silver, because it took more energy to create the same temperature change. So the specific heat capacity C of any substance is defined as the quantity of heat Q required to change the temperature T of a unit mass M of the substance by 1 degree Celsius. So C equals Q divided by M delta T, where delta T is the change in temperature. So this is the specific heat capacity, this is the heat. M, of course, represents the mass, and delta T, as I said, represents the temperature change. Thermal equilibrium. Thermal equilibrium is the state of a system when all parts are at the same temperature. That is, no part of the system can transfer energy in the form of heat to another part of the system. Now, thermal equilibrium is not to be confused with thermodynamic equilibrium. Systems in thermodynamic equilibrium are always in thermal equilibrium, but the reverse is not true, in that systems in thermal equilibrium may not be in thermodynamic equilibrium. Now, we won't really talk about this, or the differences between those two in this class. We won't deal with thermodynamic equilibrium. We will simply deal with thermal equilibrium, but I wanted to point that out. Water seeks a common level with pressures at equal elevations. Similarly, the thermometer and its surroundings reach a common temperature, with the average kinetic energy per particle being the same. So sometimes it's helpful to make these connections through analogy between temperature and pressure, which is what I've done now, I believe, twice. Thermal expansion, the tendency of matter to change its shape, area, volume, and density in response to a change in temperature. Generally, increased temperature produces expansion, while decreased temperature produces contraction. Different substances expand or contract at different rates. Consider two strips of different metals that are welded or riveted together into something called a bimetallic strip. If a heat source is put to the strip will bend. Why is that? Because the brass expands faster than the steel. Thermal expansion is used in engineering applications. Consider the displayed switch, which can be part of a circuit, such as in a thermostat. If the temperature cools too much, the brass will contract faster than the steel, forcing the switch to close, which will close the circuit and turn on the thermostat for the heater, for example. Now, when the temperature gets too hot, the brass expands faster than the steel, causing the circuit to open again. There's other examples, such as telephone wires. If you are to put up telephone wires in summer, the wires themselves will be longer than they will be in winter. So if you make them very, very tight when you put them up in summer, during winter, when the wires contract, it will cause the poles to be pulled toward each other and eventually snap. Also, dental fillings. You want to make sure that whatever substances you put in your teeth expand and contract at the same rate that your teeth expand and contract. Otherwise, the fillings will break your teeth when things get too hot in your mouth, and then when things get too cold, they will leave gaps because they contract faster than your teeth contract. Also, bridge expansion joints, concrete roadways, etc. You can look at these examples more thoroughly explained in the textbook Conceptual Physics by Paul Hewitt. Expansion of water. Liquids generally increase in volume and therefore decrease in density with increasing temperature and have average coefficients of volume expansion about 10 times greater than those of solids, meaning they increase more dramatically than solids do for the same change in temperature. Now, cold water is an exception to this rule. The density curve goes up and then down, and from the curve, we see that the water is most dense not at 0 degrees Celsius, but at some other higher temperature. What temperature? Well, let's zoom in. As the temperature increases from 0 degrees Celsius to 4 degrees Celsius, water contracts and its density therefore increases. Hence, a 4 degrees Celsius water is at its most dense. And why is that? Well, there are competing tendencies of water as the temperature increases beyond 0 degrees. On one hand, density increases because the ice crystals collapse. On the other hand, density decreases because molecules begin moving faster and push each other apart. This combined effect produces the orange curve shown. This behavior is important in nature. Ice will float at the surface of water, and cold water will float at the top of the body of water. The more dense 4 degrees Celsius water will sink to the bottom of a body of water, meaning a lake or a pond will freeze top down rather than from bottom up, allowing fish and other water life to survive during harsh winters. If water did not have this weird, odd behavior, organisms living in water where freezing occurs would be destroyed every winter. Problem 3. To say that body A has a higher temperature than body B is to say body A has more A, internal energy, B, mass, C, kinetic energy, D, potential energy. Well, we know that temperature is most closely related to the kinetic energy per particle. It's not related directly to internal energy. There is some connection. It's not related directly to mass. It's certainly not related to potential energy. So the best answer here is kinetic energy per particle. Summary. We discussed temperature, heat, specific heat capacity, thermal expansion, and specifically expansion of water. I'll see you next time.